Chapter 7 is all about energy! Something that I don't have a lot of, but my kids seem to just have it in abundance. I wish I could bottle it up. But let's get to the physics aspect of it. Alright? Energy enables a system to do work. Alright? Just think of yourself. You stay up all night, binging on Netflix or going to a party or whatever, and then you gotta get up the next morning to go to work. It's not going to be so good, right? Because you don't have any energy to work, alright? Same thing in physics, alright? Energy gives an object the ability to do work, okay? So we need to figure out what work is before we can deal with energy, alright? Well, work depends on two things, force and distance, okay? So if you apply a force to an object, like pushing a book across the table, right? You can apply force, but until it actually moves a distance, you didn't do any work, alright? So you can push on a wall all day long, but unless you can magically make that wall move, you're not doing any work on the wall, okay? It's got to move a certain distance, okay? Work is measured in joules, okay? So is energy. Alright, new unit for you. Alright, here's some examples of work and that distance and force you used. I'll let you read through that. Alright, well, simple machines can help us do work easier, right? Like a pulley system or a lever system, they can help us do work a little bit easier. Because see this pivot point right here? Alright, so depending on where we put that pivot point, alright, can make life easy or hard for us, okay? So, look at this. We got a little d and a big F. Force and distance, right? Over here we got a little f and a big D, right? So the d is the length from the pivot point on this side, okay? So if you've got a big distance, that means you can apply a little force, all right, to get work done on this side where the big force is, alright? So say, let's remember, like old cartoons, right? Where you see, maybe Wile E. Coyote jump on this side to launch the big anvil on that side to try to get that roadrunner, right? So the big anvil, that's a big weight, right? So that's a big force that he's got to lift, right? So he doesn't weigh as much as the anvil. So as long as his side of the board is longer from the pivot point and he jumps on it, his little force applied at this long distance will actually launch this big force over here. Alright? Simple machines. Work in has got to equal the work out. Alright? Which is represented by the equation here in the bottom of your picture. Alright. So, power. Alright? We all talk about power. And the thing that springs to mind is your electric bill. Right? But power is actually how fast energy is used or transformed from one type of energy to another. It can also be thought of as how fast you do work. Okay? So how fast can this girl do some work by pulling that big Humvee? Alright? Okay? Time matters when you're talking about power. Right? Time is a big factor here. Okay? Now power is measured in watts. Okay? Mechanical energy. Remember I told you everything mechanical is the big umbrella, right? So we may have little pieces under that umbrella. Same goes for energy. The little pieces under the umbrella are potential and kinetic energy. Alright? When you think of potential, what do you think of? Oh, he's got a lot of potential, right? That means he's got a lot of stored, right? A lot stored. He could go places, right? He, she, it. Same goes. Stored energy. Alright, now stored energy is based on position. Okay? We'll talk about more of that in a minute. Kinetic energy, right? Kinetic. Kinetic means motion. So this is the energy of motion. Alright? Now this roller coaster here has both. Alright? Because when you're at the tip top right here, oh, you got a whole lot of stored energy right there. And then you go over, and it's all released to motion. Okay? Now, potential energy. There's 3 different types of potential energy, but we're going to focus on just one. Gravitational potential energy. right? Means it uses gravity and at an elevated position to store some energy, right? So for example, we got a pile driver right here. That's what this thing is, right? The operator is going to crank it up so that this big weight is lifted some distance, and then it's going to hang there, all right? So he did some work to lift it up that distance, but then he's going to let it sit there. So while it's sitting there at that elevated position, it's got stored energy. All the work that was done to get there is now stored as potential energy, all right? Just waiting to be released to do some work, okay? So the higher you go, right, and the bigger the weight, the more potential energy you have, right? And here's your equations down here, right? So remember, mass times gravity gives you weight, and there's your height, okay? Here's an example of potential energy. I'll let you read through later. All right, kinetic energy, energy of motion, right? If it's not moving, it doesn't have any, right? Well, kinetic energy depends on the mass of the object moving and the square of its velocity, right? Whoops, sorry. So velocity squared, okay? So if we were to say double the speed of an object, that means its kinetic energy would actually quadruple, right? I'll talk about that down here. Right, so don't forget that square when you're doing some calculations later. Now, work and energy are related. They've got to be. They're measured in the same units, right? And we just talked about how doing work to get more potential energy. Well, let's talk about how that work is related to kinetic energy, okay? So, let's say we got a wagon that we want to move, okay? Well, to push it around to the backyard, we've got to change the velocity, right? It's sitting there, zero velocity. We start pushing on it, it's going to have some velocity, right? That change in velocity means we're also going to have a change in kinetic energy, right? Remember, you change velocity, that gives you acceleration. To have acceleration, there's a net force, right? Moving that wagon means it's going to move a distance, right? So look at all these underlined words. Force and distance, right? What is that? Work. Change in kinetic energy. So, put it all together, what do we get? Work equals the change in kinetic energy, but also the force times distance we talked about originally, right? You can calculate it either way, or you can put it all together like this to help you find a missing piece, okay? Here's an example I work out for you using that energy theorem, okay? Now, energy, like momentum, is a conserved quantity. You can't gain it or lose it. Whatever you have originally before an interaction takes place or a change has got to be what you have afterwards, okay? Here's a perfect example of that along with some videos, all right? Now, efficiency. How efficient are you at work, and how efficient is your car? How efficient is your Somali washing machine over here, right? Well, to calculate efficiency, you've got to have useful energy output divided by the total energy that was input times 100 to give you your percentage, all right? So here's an example of that along with the video, okay? So watch the videos, read your textbook, all right? Do the examples throughout this lesson, all right? And as always, have any questions, you contact me. Talk to you guys later.